Hi. So as promised, we will begin our discussion of viscosity, and the final point of this discussion will be the Navier-Stokes equation, which is essentially the momentum equation with viscosity terms included. So we will start with a bit of an intuitive derivation of the Navier-Stokes equation, especially with the viscosity terms included. So consider viscous flow between two unbounded parallel plates like so, okay? And unbounded in the following sense, this dimension, the x dimension is infinite, and the z dimension, which is into the plane of the screen, this is also infinite. Okay, so consider a viscous fluid like say honey or something, honey or maybe motor oil flowing through this, flowing in this direction. Yeah, and intuitively you can appreciate the fact that the velocity profile of such a fluid would be something like this. Yeah, so the velocity is largest at the center of the pipe. It progressively decreases, and the fluid sticks to the boundaries. This is the whole point of viscosity, right? It sticks. The flow does not slip at the boundaries. There is no slippage, right? There's the whole point. Motor oil, as the oil heats up, the people do all kinds of engineering to ensure that the viscosity stays, because you want the motor oil to be lubricating the piston, right? And so even when the oil heats up as you drive the vehicle, you want the lubrication to remain intact, right? So you want the oil to form a protective layer here and here, right? So that the piston which is moving through is properly lubricated. And the protective layer is all about sticking, no slipping, right? So because there is sticking and no slipping, the velocity vectors at the edges are much smaller than what they are in the middle. In other words, the velocity profile looks like this, and it's not flat. Okay, what does this immediately remind you of? You recall this diagram that we used to draw all the time. Here is an unbounded surface, and here is a free surface of the fluid. For some reason, the fluid is flowing this way, and the velocity, and this would be x, and that would be y, and the velocity streamlines would look like this. So there would be a gradient. We've drawn this so many different times, right? We've said this so many times. So it's essentially the same thing that we're talking about. And so now let's write down the momentum equation with viscosity for this same situation, which is the Navier-Stokes equation, right? So instead of now writing down F equals ma, let me consider simply the whatever components of F there are. Okay, and let me consider a steady state flow in which there is no acceleration. In other words, the velocity is constant. So A is 0. So therefore, the forces have to balance, right? The net F, if that's the case, for steady flow, the net force equals 0 by definition. And by steady, I don't mean non-turbulent or anything. I mean a flow which is not accelerating, which is just flowing at a constant velocity. The net force on a fluid element, of course. When I say net force, I mean net force on a fluid element, right? This is equal to 0. This is, intuitively obvious. Okay, so what about it? What are the different kinds of forces that could be acting on this kind of a, let me blow this up a little bit, on this kind of a fluid element, right? So fluid would flow along the x direction due to the pressure gradient. Pressure is dp dx. right? So if for instance the fluid is flowing in this direction, it would be because the pressure here is larger than the pressure here. In other words, there's a non-zero dp dx. So this would be one kind of force, and this would have to be balanced by another kind of force if the net force on this fluid element, on this fluid element here, is equal to 0, right? If as we said, that's the definition of a steady flow, right? So one kind of force is dp dx, and what's it balanced by? It has to be balanced by something having to do with viscosity. You get the hint, we are talking about viscosity, and so there's also, and when we talk of this, the other thing, intuitively viscosity has to do with friction, has to do with heating. Okay, viscous effects contribute to heating, and heating in our mind is generally associated with friction. Okay, so it's in that sense that I use the word frictional force. Okay, this word. There's also a frictional opposing force. So the first force we talked about was simply due to the pressure gradient. That's making the that's making the flow go from the left to right. But there's also a frictional opposing force in steady state, because that's the situation that we're considering, one where the fluid element is not accelerating. And these two forces have to balance, else the fluid would accelerate, right? So now, what is the frictional opposing force? This is the other big question, right? Recall that all our discussions are confined to what are called Newtonian fluids. And for Newton, the definition of a Newtonian fluid is one where the viscous stress is proportional to the velocity gradient, in other words, the strain. So this would be the velocity gradient. This quantity is the velocity gradient, right? And this quantity is the viscous stress. And this is very similar to pressure. It's also the force per unit area, except it's not the normal force per unit area, it's a shear force per unit area, hence it's a shear stress. And this is the velocity gradient, and this is essentially the strain. It's a stress versus strain relationship, just like what you're familiar with from elasticity. And the constant of proportionality is this quantity. This is the constant of proportionality, this mu. This is the constant of proportionality, and this has to do with viscosity. Okay, so this we've already discussed. I just wanted to remind you of this. And so this is the kind of thing that we're talking about. Therefore, per unit length in the z direction, and the z direction is into the plane of the screen, per dz, the force balance reads this. You see, mu times du dy, this is viscous stress, this is force per unit area, yeah, and we multiply a dz, right? So we have, essentially what I'm trying to do is I'm trying to get rid of the area. Dz is one length element, and then I will be eventually multiplying with dy as well. Okay, so bear with me for a second, but what we're saying is mu times du dy at some y plus dy minus mu times du dy at y, this is equal to this. This quantity is equal to d square u du square times dy by the definition of a derivative. Okay, this is you already have a first derivative here, and you divide this by a dy and you have d squared u dy squared. Okay, and I multiply that because that it was not here. So this is essentially mu times d squared u dy squared times dy. Okay, and this I'm writing down. So this is the viscous force. This is the opposing. It's the opposing sort of another way of writing it is it's the frictional force, and this is a pressure gradient force, right? And the two are balancing each other because the fluid element is not accelerating, right? There is no ma. So you can write it like this. There you go. Simpler way, the dy's cancel out, the dz was already implicit, and therefore mu times d square u dy squared is equal to dp dx. In a way, in some sense, this is it. I mean, we've already written down the Navier-Stokes equation, except this is only the force part, yeah, and you really should be putting in, you should be allowing for the fact that the fluid element can be accelerating. Okay, we wrote this down just to motivate the Navier-Stokes equation. Yeah, so more generally, we just considered one dimension. More generally, it's not a d square u dy squared. It's a Laplacian. It's a grad squared. Except, please remember that this is actually a vector Laplacian. This is not the scalar Laplacian that you're generally familiar with. This is a vector Laplacian. Okay. So with this additional term due to viscous stresses, this is what was absent in the Euler equation that we've been discussing so far, right? And you see this term has a opposite sign to the, because the two are appearing on opposite sides of the equation. The sign is different. And so the full momentum equation, in other words the Euler equation plus the viscous stress term, which we have now introduced here, the Euler equation plus the viscous stress term, which is nothing but the Navier-Stokes equation. This now reads, we were already familiar with this. This is the ma term, and these are the forces. And notice the sign of this term is opposite to the sign of this term. This is due to pressure gradient, this is due to body forces. These two we already knew from our discussion of the Euler equation. The additional term is this. Yeah? Right. So there you have it. And just by way of an aside, so this essentially is the Navier-Stokes equation, this thing. Okay. Now remember, when we were talking about the Kelvin's vorticity theorem, I alluded to this, and I pointed out, I alluded to specifically this term. Okay. Remember what we were talking about there. We were talking about water from a hose, right, which is being pointed at a wall. And generally you think of water as an inviscid fluid, or at least a very low viscosity fluid. And the water is flowing out in a laminar fashion. But we made the observation that when this laminar flow hits a wall, vortices are generated, right? Whereas there is no evidence for vortices in the bulk flow, somehow vortices are generated. And since water is more or less an inviscid fluid, this seems to defy Kelvin's vorticity theorem, which says that for an inviscid fluid, incompressible water also is incompressible to a very large, to a considerable extent. And so all the assumptions that were inherent in the derivation of Kelvin's vorticity theorem hold pretty well in this situation. But clearly vorticity seems to be generated right at the wall, yeah, where there are lots of swirling motions that are observed. So what gives? The answer lies in this term. Although in general, in the bulk flow, up until it hits the wall, this term would not be important because mu itself is very small. Right at the boundary, yeah, the water is coming to a crashing halt. In other words, the du dx and to a larger extent d square u dx square, which is what these kinds of terms are like. These become very appreciable at the boundary. Okay, so even though mu might be small, the combination of these terms, the multiplication of these two terms become important. And so this term assumes importance in comparison to what? In physics we always have to ask, this term assumes importance, yes, but in comparison to what? In comparison to the pressure gradient and the body forces. In this case, for horizontal flow of water, the body forces are not important. I mean, as in it's the same, but it becomes important in comparison to the pressure gradient forces. So one of the basic assumptions underlying Kelvin's vorticity theorem, which is that viscosity is unimportant, it breaks down just near the boundary because of the way in which the viscous terms manifest themselves in the equation. Okay? So therefore, it's not true that vorticity cannot be generated. Vorticity can be generated, and that's true only at that boundary, and that's why the vortices start forming. So we'll wrap up this discussion here, and we'll continue with our discussion of Navier-Stokes equation.